In all previous presentations, we stressed that research relies on experimental validation. This notion is so important that we end the series with additional reflections on experimental validation. For any kind of research, with the only exception of purely theoretical mathematical research, validation is mainly done experimentally. In mathematics, often results are stated as theorems, and the research contribution mainly lies in the difficulty and subtlety of the mathematical proof, which requires ingenuity by the researcher. A kind of experimental attitude may be useful here too. For example, in theoretical research, a carefully chosen experiment can take the form of a counterexample. A proof by counterexample is a way to show that a given universal statement cannot possibly be correct by showing an instance that contradicts the statement. The identification of a counterexample can provide hints to the researcher on how to restate the theorem in a more appropriate form that eliminates the counterexample. For any other kind of research, experiments are crucial to assess validity of research results. Exhaustive validation is in practice impossible, since the input space to explore may be too large or even infinite. In the case of experimental research that tries to understand some natural or human phenomenon, not all possible occurrences of the phenomenon can be tried to challenge the findings. In the case of constructive research, when researchers invent new artifacts, validation amounts to showing that they are novel and useful. We wish to focus here on two questions. First, how can we choose a validation strategy? And second, how do we ensure that validation is done properly? As for the first question, the validation strategy varies a lot across different kinds of research. For example, in physics or biology research, it may require setting an experiment in a laboratory. Physics research, in some cases, requires building ad hoc, very expensive experimental facilities. Experimental facilities can be also very expensive in engineering research, for example, requiring a wind tunnel to assess certain fluid dynamics conditions. In informatics, but also in social sciences and in life sciences, validation is often done by case studies. A case study is a research validation involving an up-close, in-depth, and detailed examination of a subject of study, the case, as well as its related contextual conditions. A case study may concern the use of a proposed new artifact in a given context, or the effectiveness of an approximate algorithm in given operational conditions. A case study may be real or simulated. A simulated case study may be implemented in simulation software environment, where possible validation situations may be generated according to different stochastic policies. The advantage of a simulated case study is that huge numbers of different situations can be generated. For example, simulation may provide an accurate analysis of precision and completeness of an approximate algorithm, assuming that the right answers are known. The disadvantage is that normally simulation implies an abstraction which may oversimplify the real case and make it unrealistic. Often, a case study is partly simulated and partly real. The purpose of a case study may be to observe the case, extract data from the observation, and analyze whether and how the data conform to the expectations. An observational case study may, for example, allow a researcher to show that a novel artifact performs well in a variety of use conditions, possibly in a real setting. Sometimes, the scope is even more restricted. A feasibility or a pilot case study may simply have the goal to demonstrate that a given proposed solution is feasible and has potential. This is sometimes a prerequisite for further research that may then lead to more proper validation. A comparative case study is done mainly to compare a research outcome against competitors. It normally assumes that a common checklist exists against which the comparison can be made. An important example is a community case study or benchmark. A community case is created by certain research communities to launch competitions among researchers working in a certain area to address a certain case. For example, solvers of logical formulae or document retrieval tools. An important property of a validation is that it must be replicable. Anybody should be able to reproduce the exact conditions under which certain results were obtained, and the same results should be obtained. A replicability case study has exactly the purpose of reproducing the experiments anew. Sometimes the goal may be to assess how the experiment remains valid while certain conditions change, or what changes in the experiment when certain conditions change. Let us now focus on the second question: how to ensure that validation is done properly? To answer this question, we need to consider that there are two dimensions: the validation question dimension and the validation solution dimension. The validation question dimension is where the hypotheses to be validated are formulated as research questions to be answered. For example, can a certain drug cause a certain effect on patients? Or, is the approximation of this algorithm acceptable? Or, does this artifact help programmers in debugging? The validation answer dimension is the experimental setting in which we observe and collect the data we use to answer the validation question. Very often, the research question takes the form of a causal relation. Does X cause Y? In the example research on culinary habits we discussed in the past, the question would be, does being an Italian imply that the person likes pasta? Or, as other examples, does the use of this tool facilitate debugging? Does this algorithm produce acceptable results? A properly done validation must ensure internal validity. Internal validity, validity inside the case, means that validation strongly supports the question and rules out alternative hypotheses. Consider the case where the validation question is expressed as a causal relation. A causes B. The experiment may show indeed that manifestations of phenomenon A, A1, A2, AI, are correlated with manifestations of B, B1, B2, BI. To claim that the experiment supports the hypothesis of causality, we need to ensure that the effects only occur if their causes have occurred before in time precedence, and there are no plausible alternative explanations for the observed covariation. To support internal validity, researchers need to perform a careful threat analysis to identify all possible ways to weaken the validation. Analysis of threats to internal validity is a prerequisite for validation and is an argument that must be discussed to support the findings when they go public. The term external validity, validity outside the case, is also used. It defines the extent to which the observed results from our validation can be generalized to other contexts, how they can apply to other possible case studies. For example, suppose that the research question concerning usability of a new tool supporting cooperative document development is validated by observing usage of the tool by college students. Can the findings be generalized to other classes of users? With this presentation on experimental validation, we conclude our discussion on research methodology.